Hello and welcome back to another video. This is IGCSE Physics Paper 2 revision. In this video, we focused on forces in motion, work, energy and power, and thermal physics. I discussed important formulas and units you need to know, some tips to ace paper 2, and then solved some past paper questions that explored those concepts. If this video does help you, please give me a thumbs up and comment below for future video recommendations. Okay, so always make sure that you know all the formulas and the units. If you know the formulas and the units, you can get a lot of marks. So we're going to start with chapter 1, motion, forces and energy. We can quickly review that speed is distance divided by time. Remember, distance is meter, time is second, so it's going to be meter per second. Velocity is displacement over time. This is also meter per second. The only difference between two of them that this is scalar while velocity is vector. That means velocity also has direction. If there is a question in which you see that the object is moving at 20 meter per second, but it suddenly turns right, the speed is same, but the direction changes. So does the velocity change? Yes, it does. Velocity has changed because direction has changed. However, speed is same. Okay, acceleration is v minus u divided by t. Acceleration basically means the change in velocity. How does velocity changes with time? The unit is meter per second square. If it's, for example, negative 2 meter per second, this represents deceleration. That means speed is reducing by 2 meter per second in 1 second. A gradient of a distance time graph represents speed. For speed times graph, the gradient will give you acceleration. For area of the graph, you should only know for speed times graph, not distance time graph. It represents the distance traveled. I have made a detailed video about all the physics graphs that you need to know. If you want to check it out, the link is in the description. Okay, now we have equations of motion. V equals u plus at. V square equals u square plus 2as. These both are for velocity. And then we have s. The s represents displacement. So it could either be u plus v over 2 times t, or s equals ut plus half at square, where u is initial velocity, v is final velocity, s is displacement, and t is time, a is acceleration. Okay, what if we're talking about falling objects? That means an object is falling down under the force of gravity. Let's say an object is falling from a cliff, so its initial velocity is going to be 0. We're going to include this value in equation 1, this one. So you can say initial velocity is 0, so we'll write 0. And then a will be replaced with g multiplied by time. Why g? Because the value of acceleration is 9.8 meter per second square. The last equation, if we want to find the distance traveled, what we can write is s equals to half gt squared, because ut will become 0, initial velocity is 0. What if the object is thrown upwards? G will be negative, v equals to minus gt, or s equals to minus half gt square. Okay, for mass and weight, remember weight equals to mass times gravity. The difference between weight and mass is weight is a vector quantity, mass is a scalar quantity. Mass is constant while weight changes with the values of g. So we have a question. The g on planet X is 1/6 of that of Earth. If mass is 20 kilogram, what is the ratio of weight on Earth to planet X? So let's find out the weight on Earth. It's going to be 196. What about for moon? It's going to be 32.7. So to find the ratio, it's going to be 196 to 32.7, 6 to 1. Without calculation, we can know weight is directly proportional to g when mass is constant. So this would be 1 to 6. Okay. Then remember, for density equals to mass divided by volume. The unit for that would be kilogram per meter cube. Now sometimes they won't give you the volume directly, but they can give you something like this. So what is the density? Density is going to be mass, which is 1000 divided by volume, and they have given you side of the cube. Remember, volume of cube is s cube, so this is going to be 50 times 50 times 50. This one would be in gram per centimeter cube. Now, for moments, remember, moments is force multiplied by perpendicular distance. And this is an example of moment. This seesaw has a clockwise moment or an anti-clockwise moment on the other direction. The unit would be Newton meter. Remember, when an object is in equilibrium, that means that this seesaw is standing like this. It's not tilted towards clockwise direction or anti-clockwise direction. It's horizontal. This means an object is in equilibrium. Values of resultant moment and resultant force is 0. Okay, if you look at this question, when we have a moment like this is an equilibrium, we can say clockwise moment equals to anti-clockwise moment. So what is the moment in clockwise direction? It's force times distance. So it's going to be 30 multiplied by 8 over 100 to convert from centimeter to meter. This equals to the moment on the opposite direction. If you notice, both of these forces are contributing to the moment in anti-clockwise direction. Then it's going to be 20 multiplied by 6 plus 2, 8, because this is the distance from the pivot, plus c times 2 by 100. Then you can equate to calculate the value of c, which is the third force. Momentum, on the other hand, is something different. Momentum is the quantity of motion. It means a moving object has some momentum. An object which is stationary has 0 momentum. So momentum equals to mass multiplied by velocity. This is the formula. So the unit is going to be kilogram meter per second. It could also be Newton second. Now there's another formula for change in momentum. This is force times time, which is impulse. This equation basically comes from F equals to ma and F equals to mv minus u divided by t. Remember, this v minus u over t comes from the equation of acceleration. We can expand this. This is mv minus mu. So remember, mass times velocity is momentum. So you can see force equals to change in momentum, initial momentum minus final momentum divided by time. Now if you bring this over there, you get impulse, and this equals to change in momentum, mv minus mu. How do seatbelts and airbags reduce injury? Now, if you have seatbelts, your change in momentum will be constant. So we'll not look at this. But what do seatbelts do is they increase the time for that momentum to occur. To move from your seat to the steering wheel, the time is increased. So when time increases, the force reduces and the force faced by the person reduces, and therefore there is less injury to the passengers. Another concept is called as conservation of momentum. This means momentum before collision equals to momentum after collision. So here we have two objects, object A and object B. They are traveling with initial velocity, so ma/ua. This is momentum before for A plus momentum before for B, md/ub. Now they are both traveling together towards right. In momentum, you have to take care of direction as well. So here we're considering direction towards right as positive. You can combine both of these masses mab, because they're traveling together, multiplied by, this is going to be multiplied by the final velocity. This is the velocity that both of them are traveling together towards right. Okay, moving on to forces. The SI unit for force is Newton. Force can bring about a lot of changes to an object. It can increase the size, decrease the size, it can change the direction. It can also be used to stretch elastic substances, for example, springs or elastic bands. If you look at this graph, we have on the x-axis we have the extension, which is the stretched length minus the initial length, and on y-axis we have the force. F is directly proportional to x and it has k. If you want to find k from this graph, remember k is going to be the gradient. This region where it's a straight line is called as elastic region, and the region beyond that is called plastic region. Hooke's law is only obeyed in the elastic region. After that, in the plastic region, is not obeyed anymore. The relationship is not linear. The point until which it is obeyed is called as limit of proportionality. After that, the line becomes curved, maybe it broke, or it's permanently deformed. Now we can look at energy, work, and power. They are related to each other. Remember, work done equals to force times distance. Work done is always written in joules. It can also be written in kilojoules or megajoules, so make sure that you convert them. Force is Newton and distance is meter. They also have other units, so convert them appropriately. So work done equals to, when you apply a certain force, how much is the distance that is moved by an object. Now in some cases, for example, if you're pushing the wall, you are applying force to the wall, but the distance is 0. The wall does not move. So in that case, work done is going to be 0. Work done is also called as energy transferred. For example, if you look at a ball which is falling through a height, work is being done to bring the ball down, and energy is transferred from gravitational potential energy into kinetic energy. Now, rate of work done is called as power. So, joules over second is known as watts. You can also write this as energy transferred per unit time. Okay, we have kinetic energy and gravitational potential energy. The equation is half mv square for kinetic, and for potential is mgh. Sometimes both of them can be equated. That means, again, for a falling object, as an object is falling down, its gravitational potential energy is being converted into kinetic energy. Initially, GPE is max and kinetic energy before falling is 0. And then right before hitting the ground, kinetic energy is max and gravitational potential energy becomes 0. So this is also the principle of conservation of energy, because no energy is lost, it's only converted from one form to another. So we can say they're both equal in value. On this equation, we can write it as half mv square equals to mgh. Now both mass is same because we are talking about the mass of the ball. The mass can be cancelled, and we can write this as v square equals to 2gh. So if you want to find the velocity of the falling object but you don't have the mass, you can use something like this. You don't have to memorize this equation, just know that you will equate both of these energies. So efficiency is the ratio between useful energy or total energy. Multiply this by 100 because the unit is in percentage. Efficiency can also be written as useful power over total power. Basically, how much energy we are giving versus how much energy is being actually used to do the process that you want to do. That is efficiency. If it's 100% efficient, useful energy and total energy will have same value. Okay. Now, pressure equals to force applied per unit area. What is the unit of pressure? It's pascals. We have another definition for pressure, which is height rho g. Again, the unit is a pascal, but this is specifically for liquid pressure. So for example, if you have an object which is submerged in a liquid, could be water, so you will write g as 9.8. And what about density? Density of water or oil or whatever the liquid, that is here. So for example, if it's water, it's going to be 1000 kilogram meter cube. And then you want to know the height. So height is the distance from the top. It's not the distance from the bottom up, okay? If an object is deeper in, for example here, this is facing more pressure because the height is greater. The surface area of the jar or the width of the jar has no effect on the pressure. It only depends on height, not the surface area. So this one will experience less pressure compared to this because this distance is greater. So terminal velocity is basically the velocity at which a falling object experiences zero acceleration because the resultant forces have been balanced. So you can see initially this was an object which is falling down, and the only force that it experiences is weight. It's falling down due to its weight and it has constant acceleration. Then you have resultant force acting down. After some time, there is also an opposing force, which is drag. So if you see, the resultant force will reduce because it's going to be W minus drag. Resultant force reduces. Resultant force is directly proportional to acceleration. So because the force reduced, acceleration will reduce as well. What happens after some time? The opposing forces become equal. Weight equals to drag. So if you find the resultant force, you have to subtract both of them, right? Because they're in opposite direction. If you subtract them, they're going to be 0. Since resultant force is 0, acceleration is 0, and the object is now moving at terminal velocity. Terminal velocity depends on the mass and surface area. If the mass is greater, terminal velocity will be greater. Surface area, however, reduces terminal velocity. For example, if you have a big beach ball compared to a small tennis ball. Alright, now we will solve some past papers covering these concepts. So first, a student uses a meter rule to measure the length of a sheet of paper. Which measurement is shown to the nearest millimeter? Okay, so remember 1 millimeter is 10 times 10 power negative 3 meters. So since it's we have 3, we need to have 3 numbers after decimal place. So this is going to be 0.293 because we have 3 numbers. 1 is B. Second, a rocket travels with an average speed of 6 km per second for 2 minutes. What is the distance traveled? So speed equals to distance over time. Therefore, distance is going to be speed multiplied by time. Speed here is in kilometer per second. Time needs to be converted into seconds. It's in minute. So multiply by 60. You'll get 6 times 2 times 60 is going to be 720, and you'll get kilometers. Therefore, the answer is C. Now, the diagram shows the vertical forces acting on a ball as it falls vertically through the air. The ball does not reach terminal velocity. Which row describes what happens to the resultant force on the ball and what happens to the acceleration as it falls through the air? Okay, so we know resultant force and acceleration are directly proportional. The equation equals to F equals to ma. If force is reducing, so is acceleration. So it's either going to be A or D. Now, what is happening to the resultant force? As the object is falling, air resistance is increasing, so the difference between the two is going to be less. Let's say weight is 20 Newton, acceleration is 2. So the resultant force here is going to be 20 minus 2, which is 18 Newton. After some time, the weight is again same, but there is air resistance increased. Now let's say it's 4 Newton. So resultant force is going to be 20 minus 4. It's going to be 60 Newton. So you can see as the object is falling, the resultant force is reducing. So it's going to be A. A coconut falls from a palm tree. At X, it has just started falling. Y is the point before it hits the ground. What is the acceleration of the coconut at X? And so we don't have to look at air resistance. The object is falling due to gravitational force of Earth, and the value of G is 9.8 meter per second square. So it's constant whether it's at X or Y. Therefore, the answer is C. Next, a car is driven round a bend in the road at constant speed. So you have a car, direction of the motion of car. What is the direction of the resultant force of the car as it is going round the bend? So this is a circular motion. In circular motion, resultant force is towards the center of the circle. And this is the object here. So you can see the car is perpendicular to the force. Therefore, it's going to be perpendicular to the motion and towards the inside of the bend. Which equation gives the momentum change of an object? mv minus mu equals to force multiplied by time. This is the impulse, so the answer is D. Which statement about the use of nuclear fuel as an energy source is correct? The energy which comes from radioactive elements. It obtains its energy from the sun. That's wrong. It does not. That is solar energy. It has no environmental impact. That's also wrong. Nuclear power stations do not need turbines. That's also wrong. The only correct answer is D. The energy is released by nuclear fission when a larger unstable nuclei are broken down into smaller ones. This is called nuclear fission and release energy. They're broken down and release energy. Next, the diagram shows an object of mass m being projected with speed v from point P to Q on top of a cliff at height h. The object does work W against air resistance as it travels from P to Q. Alright, to answer this question, remember that the law of conservation of energy at P equals to energy at Q. So what is the energy at P? It's going to be half mv square. We only have kinetic energy. Potential energy is 0 at this point. Energy at Q. So here, A, we have the kinetic energy at Q, so Ke at Q. And then at Q, we also have some potential energy. So this is going to be mgh. Plus, there's also some work done against air resistance. So we'll also write plus W. Now we're supposed to find the kinetic energy of the object at point Q. So we can rearrange this equation. Half mv square minus mgh minus W. And if you see, that is going to be D. So here this looks like an efficiency diagram. The diagram shows a stand key diagram for an electric drill. What is the total wasted energy shown by the diagram? Okay, so this is the input energy, all of this. Then most of it is converted into kinetic energy, but some of it is lost as thermal energy and sound energy. So they're asking, what is the total energy wasted shown by the diagram? This is going to be this one, right? And they said the distance between two lines equals to 40 joules. So we can count the squares. So we have one square here, 1, 2, 3, 4. So we have 5 squares in total. This is going to be 40 multiplied by 5, which is going to be 200 joules. So the answer is B. Okay, now we can quickly review thermal physics. So first, this equation equals to Q equals to mc delta theta. This equation focuses on specific heat capacity. C here represents specific heat capacity. It means what is the amount of energy needed to increase the temperature of 1 kg substance by 1 degree Celsius. For example, if you have a aluminum block that has 1 kilogram, how much Q should be there, how much energy in joules you need to give to increase the temperature by 1 degree Celsius. So this is the formula where Q is the energy absorbed. Okay, energy absorbed when you're increasing the temperature, but it can also be for reducing the temperature by 1 degree Celsius. At that point, it's going to be energy released. The unit is joules. M is the mass of substance in kilograms. C is specific heat capacity. The unit is joules per kilogram degree Celsius. And a delta theta is change in temperature, which is final temperature minus initial temperature. The unit is either in degree Celsius or in Kelvin. And then we have two more equations, Q equals to mLF and Q equals to mLV. LF is the latent heat of fusion. This is the hidden heat. This is basically the amount of heat required to change a substance from a solid to liquid at its melting point without an increase in temperature. Q is again in joules, mass is in kilograms, and LF is latent heat of fusion is going to be joules per kilogram. On the other hand, LV is the latent heat of vaporization. This is the amount of heat required to change a substance from a liquid to a gas at its boiling point without change in temperature. Both of these processes involve energy changes, but there's no change in temperature. Okay, so now we can look at these points. Internal energy of a substance is kinetic energy and potential energy. When the temperature rises, for example, from 20 to 30 degrees Celsius, only the kinetic energy is increasing. The temperature is increasing, the particles are vibrating faster, so there is an increase in kinetic energy. However, when there's a change in state over here and here, when, for example, ice is melting or the liquid is boiling, the temperature is not rising, but the particles are moving away from each other. As they're melting, the molecular forces are being broken, the intermolecular forces are being broken, and potential energy is increasing. Alright, so we can say that our internal energy depends on 4 factors, okay? First, it depends on temperature. If the temperature is higher, it's going to have more kinetic energy. Second, it also depends on the state of matter. If, for example, gas particles have the highest internal energy. Now, what about the mass of substance? If the mass is greater, more mass means more particles, so more internal energy. And then finally, specific heat capacity. Internal energy depends on specific heat capacity because it says how much energy is needed to change the temperature. So if a substance has very high heat capacity, it's going to have high internal energy as well. Now, to change from Celsius to Kelvin, add 273. One more important rule is Boyle's law. This means that when temperature is constant, pressure and volume are inversely proportional. For example, if you want to find V1, it's going to be P2 times V2 divided by P1. Now let's solve some questions based on that. So they're saying an elephant weighs 45,000 Newton. It stands with all 4 feet on the floor. The average pressure on the floor due to elephant foot in contact is 34,000 Pascal. What is the area of each foot? This is our equation. They're asking for the area. So area is going to be force over pressure. So the entire force is the weight. This is going to be 45,000 Newton divided by the average pressure. So this is 34,000 Pascals. So we get 1.32 meters square. Now this is area of all 4 foot, okay? So we need to find the area of each foot, divide this by 4 and you get 0.33. So the answer is going to be B. Now, some air is trapped inside a metal container with a tightly fitting lid. Okay, this is heated strongly behind a safety screen. The lid is blown off by the increased pressure of the air inside the container. What causes the increase in pressure of the air inside the container? Now what happens is when we heat a substance, temperature increases and their kinetic energy increases, so they move more quickly. This is the most appropriate answer. Next, a very hot mug of coffee is near a large unheated swimming pool holding 2 times 10 power 6 kilogram of water. Which statement is correct? If the mug of coffee is dipped in the pool, the coffee will lose much more internal energy than the water in the pool gains. That's not correct. The amount of internal energy lost by the coffee equals to the internal energy gained by the water in the pool, so A is wrong. The internal energy of a substance depends only on its temperature. No, it depends on the state of the substance, whether it's liquid or gas. So no, definitely not just temperature. C, the internal energy of the water in the pool is lower than the internal energy of the mug of coffee. Okay, so we know that the temperature is high for the mug. Temperature is high, so the internal energy should be greater. But if you notice that this is just a very small mug of coffee compared to the pool, who has 2 times 10 power 6 kilograms. So the mass of water in the pool is so much higher. When the mass is high, internal energy will also be greater. So that means internal energy of the pool is going to be greater, not lower. Finally, when the temperature of the mug of coffee falls, its internal energy will decrease. Yes, that's correct. The kinetic energy will decrease. So does so internal energy decrease as well. The answer is D. Now, a student measures the mass of water in an open container for 2 hours. Okay, so the container is kept in a warm room. The results are in the table. So the mass of water initially was 33.9, and after 2 hours, it reduced to 22.5. Why does the mass of water change? The water evaporates, freezes, condenses, boils. Obviously, this is kept in a warm room, so it could either be A or D. The reason why it's not going to be D is because water only boils at a boiling point. Evaporation can occur at any temperature below it, so the water is evaporating, and that's why the mass of water is being reduced. Water boils at 100 degrees Celsius, so obviously the room is not at this temperature. Next, a 1 kilogram block of aluminum requires more thermal energy to raise its temperature by 1 degree Celsius than 1 kilogram block of copper requires. Why? Because okay, now whenever we see something like this, to raise temperature by 1 degree Celsius, it's because they're talking about specific heat capacity. So they're saying aluminum requires more energy, so its specific heat capacity is going to be higher. 15 is C. Next, a block of ice is at a temperature of negative 100 degrees Celsius initially. Energy is applied at constant rate. The graph shows how its temperature changes. At which points have the ice completely changed state to water, and all the water has completely changed to steam. Okay, so you have to say which point it changed to water and at which point it changed to steam. Okay, so you can see that this is ice. Here between 1 and 2, ice is melting. So at point 2, it has completely melted. That's why the temperature began increasing after this. To completely change to steam is obviously going to be point 4, because after that point, temperature began to increase. Change of state has finished.